work solutions to the 3 typical exam questions. Make sure you're on the same. The question 1 was the nameplate on an AC electric motor indicates that it's designed to connect to 600 volts. So 600 volt, 50 hertz line, full load current 12.8 amps, the power factor 0.75. So A says sketch the power triangle. So getting those 3 things right on there would be worth some marks. Yeah. Represent the meter readings and determine the active and reactive power absorbed by the motor. So apparent power 7680 VA, yeah, is that what you got?
Oh yeah.
Yeah. And 5,760 watts using trigonometry. Hang on, see if I've got another copy, man. And Q using Pythagoras 580 var. 5,080 var, sorry. Yep. Is that what you got, James? Yep. B. So there's 9 marks for doing that. Yep. B. Determine the in-phase and out-of-phase components of current, IP and IQ. So the in-phase component, the part due to resistance, can be garnered from the power divided by E, because power is current times voltage. Rearrange that, 9.6 amps. Yep. And then for the current due to Q is equal to IQ times E, so we rearrange that, we end up at 8.47 amps. Yeah, no issues there? I think, unless that come out as, I think if you do 3 to 4 significant figures, that's plenty. Yeah, alright. C, which is determine the phase angle between the line current and line voltage. So that's cosine of, use the cosine with IL and IP. Arguably you could use the powers to find that. That's the same angle, and so that would be equally valid to use Q, P, and S, and the so P and S and the cosine, or Q and S and the sine. Any way that you can find that angle would give you further 3 marks. Then calculate the, so all of that is relatively straightforward if you understand the 3 different powers and the currents being in and out of phase with each other. Then that moves on to something that makes it gets a little bit more tricky in terms of adding some power factor correction. So calculate the reactive power needed from a power factor correction capacitor in order to improve the power factor of the motor to 0.9. So this is where you need to be drawing a new revised diagram, that you're going to add to your diagram some QC that's going to pull the overall Q down from Q old to Q new, and that you can find Q obtained from the capacitor by, you know, the old Q. What does the new Q need to be for the power factor to be 0.9, sorry, and therefore you can find QC. So you find the new Q using trigonometry. We find out what the angle is, use the tangent. I got the new Q to be 2784 var. Yeah. So therefore, the Q due to the capacitor It's 580 minus 2784 is 2296 var. Full marks for that. And then it says, lastly, determine the new apparent power. So you use the old P, because power doesn't change, with the new Q squared in Pythagoras theorem to get 6201 VA. Yep, agreed. New line current, get from the S being I times E, rearranged, new line current is 10.3 amps. So we've gone down, by improving the power factor, we've gone down by from 12.8 to 10.3. And there's that caveat at the bottom that in the actual exam, there might typically be formal marks awarded to use your knowledge to explain the benefits of power factor correction on that system. Alright? And I could put that in any of the questions that involve power factor correction if I choose to. Alright? So that's about you knowing that reduces the current so you can use smaller cables and there's less power loss, that kind of thing. Yep. Alright, so we're okay with question 1. Question 2 involved, first thing, it's about one of these multiple loads diagrams. The first thing is you've been given the motor in terms of, or one of the motors in terms of a power rating and a power factor. And so you need to find out, for your diagram, you need to know what the VAR is. So again, using the triangle, we've got 6.7 kilowatts. You've been given a power factor of 0.65, so the cosine of the angle is 0.65. So we find the angle, do some more trigonometry, and end up with 7845 VAR. Yeah, which proves what it says there. 6 marks for being able to do that. Draw the system. So drawing that is also included in those marks. So you need to make sure that you show the arrows the direction of the flows of power. So you're drawing VARs for inductive loads, drawing kilowatts for plain heating loads. Motors have drawn both power and reactive power, and capacitors are, the arrows are going back in, they're giving reactive power back. Then you know that determine the total active power, you do that by adding all the individual powers up, 34.4 kilowatts. Determine total reactive, add all the Q's up, making sure the capacitive ones are negative, total 44.1 kVAR. Find an S, using Pythagoras, 55.9 kVAR. No issues. Power factor, we can get from P over S, 34.4 over 55.9, 0.615, and then using the S formula for S is equal to E times I, we can find the line current. Now it's talking again about it, some more power factor correction added to the system, such that the power factor is going to improve to 0.9 from 0.615. So that's a diagram showing the whole system and how it's being affected by this addition of a third capacitor down here. So again, we've got an old Q, a new Q. We can find the new Q, which I got as 16.6 kVAR. Yeah. Take that away from the old to get the Q provided by the capacitor, 27.5 kVAR. That allowed me to calculate a new S, 38.2 kVA. And then new current IL as S new over E, 50.9 amps. So in that question, again, I could choose to put the bit about power factor correction and its benefits in that question, and we've improved the current from 74.5 amps down to 50.9. And one thing you must remember is if you reduce the current by half, you reduce the power loss by a quarter in the cables because of the I squared R relationship. Yep. Question 3, which didn't really come in until we finished the stuff on faulted three-phase systems, but sketch a label diagram. So we got 3 heaters of equal power rating connected in delta configuration to a three-phase star-connected generator. Line voltage 650, 60 Hertz. Line current is measured to be 18.6. That is as connected. I had a query, I think that might have been James last week or the week before, as to what happens when it's changed into star system. Well, that 18.6 amps is no longer relevant then. That's just in the as delta connected system described at the top. And we talked about that, James, didn't we? Alright. So, I sketch a label diagram. So that's what I would expect to see, that you show a star connected generator, the delta connected load, and the information given that the current flowing in the lines is 18.6 amps and the line voltage is 650 volts, 60 Hertz. Yeah. So it says determine the phase current for each load. Well, we know that for a delta system, I phase is I load over root 3. That's something that you're going to need to remember. Yeah. 18.6 over root 3, 10.74 amps. Once you've done that, you've got the current through one element, then you can use the line voltage, because the line and phase voltage are the same in a delta system, divided by that current to get the resistance of each load. Yeah, 60.5 ohms. Power for each phase, I've used I squared R, and I get 6979 watts. Yeah, total power, multiply that by 3, 20.9 kilowatts. And it says show that the total power dissipated is 20.9, so we've shown all the working to prove that. Yeah. No issues with that, no? Now consider the same load connected in star configuration. So we've got the same generator, we've got the same line voltage, we've got a neutral connection to the same three resistances connected in star configuration. So we've now got a phase voltage which is 650 over root 3. Yeah. The new line current is the phase voltage divided by R. So we've gone 650 over root 3, 60.5. I would prefer to see it used like that rather than calculate what 650 over root 3 is and round it. More professional to do it that way. So you're carrying everything through. 6.2 amps. New power for each phase. Again, I've used I squared R, 2326 watts. The new total power is 3 times that, 6.98 kilowatts, which compares with the delta system of 20.9. Yeah. So about a third. And you connect the same load in star as opposed to delta. Still quite plain that the line current, well, the line current is that, because line current and phase current are the same, but the line current here is nowhere near the same as that 18.6 amps. In fact, it's 3 times a third of it. Yeah? Alright. C. Carry out suitable calculations to show that this balanced load means that no current flows in the neutral. So we make this statement that by Kirchhoff's current law, the neutral current is equal to I1 plus I2 plus I3. They're all 6.2 amps, one at 0 degrees, one at 120, one at minus 120. Or if we had Mike in a room, we'd have one at minus 240. We had a few laughs about that last week. But that's still the same thing. Turn them into rectangular form, add them up, and you're approximately equal to 0 plus 0j. The j's cancel out, proving there's no current in the neutral. Well, we've done that on the rig system and proved that as well. D. Consider the case where the load on each phase of the system becomes unbalanced by the connection of a heating element of double the resistance of the original heaters on two of the phases. So I've taken 121 ohms as being double 60.5, and I've put that on phases 2 and 3 for want of better ones to choose. If you choose different ones, if you choose 1 and 2, then your neutral current is going to have a different angle, but the magnitude should still be the same. Current I1 is the same as before. I2 and I3 in magnitude are going to be equal. They're going to be 650 over root 3, which is the phase voltage, divided by 121 ohms now, exactly half the current in magnitude. We take them to one with an angle of 120, one with an angle of minus 120, again find the rectangular values for them, add them up, and I got 3.1 at angle, or 0j, which is angle 0 degrees. Yeah? Okay? And that's them 3 questions, which I'm not hearing that there were too many problems with them. I know you've got your notes to look through at the moment, right? But still haven't got stuck, which is good. All right? Everyone happy with that? And we'll have more example questions to do between now and the exam. But I always fit them in the class time, so we haven't been... That's always intended to do those 3 at this stage, rather than leave everything till the end. All right?